and welcome you today to our webcast and introduce you to Frank Monforti, our presenter. Dr. Frank Monforti is the Director of Forecasting Solutions at Itron, where he is an internationally recognized authority in the areas of real-time load and generation forecasting, retail portfolio forecasting, and long-term energy forecasting. Dr. Monforti's real-time forecasting expertise includes authoring load forecasting models used to support real-time system operations for the North America system operators, California ISO, New York ISO, Midwest ISO, ERCOT, and the IESO. His recent efforts include authoring embedded solar plant and wind farm generation forecast models used to support real-time operations of the California ISO. Dr. Monforti founded the annual ISO TSO Forecasting Summit that brings together these groups from around the world to discuss forecasting challenges unique to their organization. Here at Itron, he directs the implementation of our retail forecasting system, which includes efforts for retailers operating in the United Kingdom, Netherlands, France, Belgium, Italy, Australia, and the United States. I'm going to go ahead and turn things over to Frank, and again, please feel free to type your questions in the Q&A tool, and thanks again for your attendance. Frank.
Thank you, Becca. All right, well, welcome, everyone. Today, the specific topic we're going to talk about is a relatively new problem in the industry, and it has to do with the proliferation of rooftop or embedded solar generation panels and the impact that's having on short-term forecasting and obviously on system operations. You know, I kind of view what we're doing as sort of a turning point in the industry. I mean, for some of you who've been in the industry for a while, you know, remember back in the late 70s, early 80s that end-use forecasting came to the forefront because of a push towards energy efficiency incentives and standards, which was primarily driven by, you know, sort of oil prices going skyrocketing. And then the next big turning point was when we went through industry restructuring. And what came out of that were sort of new players in the market. There were energy retail suppliers who needed to have daily or day of forecasts of the demand for power or gas for their customer portfolio. And then there were independent system operators and transmission system operators, which all of a sudden became organizations, and they're primarily tasked with running the grids and keeping them going. And what came out of that also in conjunction with that was the use of neural networks for handling the short-term forecasting problem. Now, the current thing is what we're seeing is with the renewable resources, in particular the grid-connected wind and solar generation, is that there's a new interest in how do we handle forecasting when there are these renewable products in place. So that's sort of, we're at a turning point, and let's kind of talk through how we got here. So what this chart shows is this is the EIA's projection of generation capacity by type. And in particular, what I want to focus on is the blue line and yellow line in the graph. And what that is, that's the cumulative, those two are the cumulative installed capacity of wind and solar generation. And as you can see, back in 2005, this wasn't much of an issue because collectively there was, you know, a little under 2% of the total worldwide generation was coming from wind and solar generation. But as we rolled into 2013 and as we continue to advance towards 2040, that percentage of the total generation mix that can be assigned to wind and solar is growing at a fairly rapid pace. So in fact, the whole topic that I'm going to talk about started about 5 years ago in Belgium with one of our energy retailers who had a significant amount of behind-the-meter solar generation in their portfolio, and they had approached us about how we could handle it in their forecasting tool. That since the Belgium place, then we've also have stumbled into this problem now in both Australia as well as in North America. And so what's driving the renewable market is nothing surprising. It's a movement towards reducing emissions worldwide. There's also concerns that kind of gets us off being oil-based or fossil fuel-based generation. And what has come out of the sort of the last several years, what we're starting to see is an increased awareness renewable resources. I think a lot of people are aware of wind, but now the solar is starting to come into the forefront. This slide here kind of illustrates what the increased awareness is driving. This is a website that the California ISO publishes once a day. And what it does is it presents up their best estimate of what the grid-connected solar and wind generation was as a proportion of the total generation that they use to meet the loads for their operating region. So this is something that's published every day. You can go look at it, and so this is becoming a very topical idea in the industry. And what's more important, and you can probably barely see it, but in the upper right-hand side of the slide, I've got 33%. So for the state of California, that is the target we're shooting for. So of the total generation, we're shooting for 33% of that generation to be supplied by renewable resources, which is a significant proportion. All right. So what is this doing from the perspective of a grid operator? Well, there's sort of a couple. The main concern is that this type of technology, wind and solar, does not produce the same sort of stable, reliable generation output that operators are used to when they're dispatching, say, gas or coal or nuclear. And this slide gives you an idea of that volatility. Here are 5 consecutive days for a single wind farm, and as you can see, the generation goes everywhere from, close to 650 megawatts all the way down to 0 megawatts. And the ramping of that generation from being on to off and from off to on is very steep. The next slide gives you, this is the solar generation output. So these are 11 grid-connected solar plants. So these are large, either solar panels or sort of heating type generation plants. And what this shows is the volatility around just the average, and we computed the average. But you can see how the generation, even for a set of plants that are within a fairly close location to each other, can really vary quite a bit through the course of a day. So there's a lot of volatility that comes with the solar and wind. Now, what the California ISO has done, and some of you might have seen this, is they came up with this stylized chart called the duct chart to illustrate some of the operational concerns that they're facing. The first thing to notice is what they call steep ramp rates. And in particular, what they're really concerned with is sort of the afternoon fall off of the wind and solar. That fall off the wind and solar in the afternoon is leading to a much steeper ramp up in what they see as load than what they have been working with before. That means they have to have fast-acting fossil fuel-fired generation in order to match that fall-off in the wind and solar generation. The other part, though, which is kind of a key part, is because of the variability of the solar and wind generation, there is the potential for over-generation. Specifically, if you're an operator and you're facing this sort of potential swing in wind and solar generation, you know that you need to have an offsetting amount of fossil fuel fire generation parked and ready to go in order to cover the cases when the solar or wind generation fall off. So you almost could have twice as much generation parked and online than what you would just to cover the uncertainty in the wind and solar. So for those people who probably think that the duct chart is not real, here's another website. This happens to be in Hawaii, where what they show is the prior day actual solar and wind generation against loads. The dark blue line is the net load, so what the control room saw. The light blue line is what demand for power was, regardless of how it was served. And so the dark blue line has that sort of duct-shaped signature. So although the duct chart that the California ISO produced was in a stylized fashion, it's not too hard to find real-life examples where that does happen to the net load shape. You do start seeing the duct chart. All right, so There's been a lot of work done over the past 10 plus years on wind generation forecasting, well documented, and there are some very major commercial vendors who do a very good job in forecasting wind generation for, wind farms or individual turbines. Probably over the last 3 years or so, there has been an equivalent amount of effort being pushed towards forecasting solar generation. And in particular, the effort there has been focused primarily on what we call grid-connected generation units. So these are large solar panel farms or these sort of heat collecting type farms, and then which collect the heat from the panels, heats up water, and then drives that through a steam generator. Fixed locations makes it a lot easier because you know where they are. So the predominant approaches to trying to forecast the generation out of these plants range from the top left graph, the satellite imagery. So here the idea is you can get, an image of cloud cover over a fairly broad area. You can then digitize that cloud cover image or the satellite imagery into like 1 kilometer by 1 kilometer squares. You can then color code the kilometer, any shaded from 0 to no clouds, to 10 being very, very cloudy. And then if you compare one image to another image, maybe taken 30 minutes later, and do a little vector math, you can project the density and the speed and the movement of clouds, and that helps forecast solar generation. A competing approach has been the middle one, which is eye in the sky. It's the same kind of idea, except instead of relying on satellite imagery, what you do is you have a land-based camera that's looking upwards. It takes pictures. Again, you can digitize those images, do a little vector map, and you can project where clouds are moving and the speed at which they're going. A third area that is starting to pick up a little bit of steam is the bottom graph. And the idea here is as people deploy solar generation, not just at power plants, but also sort of rooftop solar, to the extent that we can start measuring the generation output from each of those points, we can digitize that sort of network or mesh of collection points, so metering points, and do sort of the same vector type approach to the map to try to project where the cloud covers are moving. So that's another approach that's people are starting to look at, which is where we're using sort of the real-time metering for locations that have embedded solar generation and using that metering in lieu of having imagery. So those are sort of the state of the art, and there's lots of conferences. The DOE has funded quite a bit of work in this area, so there's lots of places to go and get up to speed as to who are the major players and what they do in this area. All right, what we have found, and now we're coming from the load forecasting perspective because our clients are the system operators and they use the load forecast we provide them in order to run the grid. What we're starting to see is a different type of problem than the grid connected problem. And that problem has to do with the behind the meter or rooftop solar installations. What the grid control room sees is what is the net demand. So you have in this little stylized slide, what you have is sort of total demand for power, and that flows in. You then subtract off what is the behind the meter solar generation, and what the control room then sees is the net effect. So they're seeing the net load after you've net out the behind the meter generation. Now, 5 years ago, there wasn't a big difference between what was true demand for power and what was the net effect. But as the penetration of behind rooftop solar grows, there is an ever increasing wedge between demand for power and what the grid operators see as the total or net load. Now, in the state of California, we have roughly, probably a little over 1,800 megawatts of behind-the-meter solar generation. That 1,800 megawatts, because it can swing from 0 to 1,800, roughly, has quite a bit of impact on the loads that the control room see. The loads that the control room sees also happen to be the loads that we build our statistical models on. So because of this increase in behind-the-meter solar generation, is now having an impact on our models, and that's where we have gotten involved in this whole sort of renewable discussion. So what does behind-the-meter generation do to our load forecast? So, and this is kind of the way you have to kind of think about, for primarily what we use is regression and neural networks. But if you think of regression neural networks at a very high level as nothing but averaging historical loads, what we're finding is that as the penetration of behind-the-meter generation grows, what we measure as load, what the control room see as load, is on average getting smaller. Now, that average, we're bouncing around it because the clouds come and go, but on average, we're getting lower and lower net loads. That implies if we fit a model, or a statistical model, and normally we'll estimate a model over, say, 2 or 3 years of historical data, the model, which is in essence an average of the historical load, will reflect in its coefficients, in the variable coefficients, it's now going to reflect the average amount of behind-solar generation that has occurred over that estimation range. So if the average amount was 100, that 100 would be embedded in our model coefficients. What that means is our load forecast models, because they have embedded the average amount of solar generation, will provide biased forecasts. On cloudy days, because we're expecting an average amount of solar generation, on cloudy days when we have 0 to very low solar generation, our load forecasts are going to be too low. On sunny days, again, because our models are synced to the average solar generation, on sunny days when we have a lot of solar generation, our models are going to fit to or predict too high. So I have a simple example of how this works. So very simple example, 10 days. The demand for power, true demand for power, is going to be fixed at 1,000. So every single day we're going to actually use 1,000 kWh or megawatts. On day 0, it's very, very cloudy, so we produce 0 behind-the-meter solar generation. On day 10, we have the sunniest day, and we maxed out at 450 megawatts of solar generation. The middle column, what I'm calling net load, is what the control room sees over these 10 days. So on the very cloudy day, they see 1,000, so they see the true demand. Conversely, on the very sunny day, they're seeing 550 megawatts because the other 450 megawatts has been essentially delivered by the behind-the-meter solar generation. Now, over this little example, the average load is 775 megawatts, and the average solar generation was 225 megawatts. All right. So what does that mean from a perspective of forecasting? Well, again, if our models are just the average, predict the average, our model is going to forecast the average load, which in this case is 775 megawatts. So every single day, what we provide as a forecast to the control room is a forecast of demand for 775 megawatts. Now, on cloudy days, when there's no behind-the-meter solar generation, our forecast of 775 is going to fall short of the 1,000 megawatts of true demand. So we're going to under-forecast cloudy day demand. Conversely, if I go all the way to day 10, where I have the most solar generation, again, my forecast that I've handed to the control room is 775. What they're going to see is the net of 550, and we have, in that case, over-forecasted demand for power. So this is the impact that the behind-the-meter solar generation is having on our load forecast models. And we are seeing it, not only at the California ISO, but also work that we have done with the Australian market operators, as well as some of our energy retail clients in Europe. They're seeing a consistent bias in the forecast. So the key takeaway here is that if there has been significant penetration, which, as I said, in the state of California, there has been, we're up to 1,800 plus megawatts of behind-the-meter solar generation. When we estimate our models over the historical time series, we're going to we're going to effectively have embedded in our estimated coefficients the average amount of behind-the-meter solar generation that took place over that time period. That is going to lead to a bias of being too low on cloudy days and a bias of being too high on sunny days. The key point here is we can't ignore this problem, because as the penetration of behind-the-meter solar generation grows, our bias potential grows with it. And so we can't ignore the problem. We have to actually do something to address it. So the two sort of modeling solutions that we have implemented for our clients are the model it directly. And the model it directly, essentially what we're going to do is we're going to put into our short-term forecasting models a variable that is our best estimate and forecast of what the behind-the-meter solar generation is in that given hour or in that given 15-minute period. The alternative approach is to reconstitute the load data. And effectively what this does is it says, give me my historical load data that I've measured and add to it or add back to it our best estimate of what the behind-the-meter solar generation was. Then what we'll do is fit the same load forecast models we've used in the past to the reconstituted data. That should then give us a forecast of total demand for power, regardless of how it's met, and then we can subtract off from that load forecast our forecast of embedded solar generation. Now, we're modelers, so the model direct it made most sense to us because we want the data to speak. You know, we don't want to necessarily impose structure onto our models. We want the models to come through. So the model direct approach is something that we put together working with the California ISO and the two Australian market operators, the AEMO and Western Power. Initially, what we were using was cloud cover forecasts in order to develop our forecast of behind-the-meter solar generation. That was effectively what we were using was the weather concepts that both these operators, all three operators were getting currently from their weather service providers. We were just using cloud cover forecasts to help drive another part of it. Now, recently, the California ISO has contracted with a third party, and that third party is providing them a forecast of embedded solar generation directly, and then we're just going to use that forecast in our statistical models. And then there's a handful of other ISOs, both in North America as well around the world, who are also evaluating this type of framework. So what we do when we're modeling directly, we start with our short-term forecasting model, and what we're going to do is modify it by adding in a variable that accounts for the behind-the-meter solar generation. All right, that looks something like this. We have our standard model. We have, fortunately, Newton and Kepler and a bunch of other people have given us all the math we need in order to develop a time series of solar generation, and we simply drop that time series into our models. Now, in principle, what will happen is by putting that variable in our models, we're freeing up the other variables, like our January binaries or July binaries. We're freeing them up to not have to account for the impact of the behind-the-meter generation. We're letting this one variable do all that work. If we do get it right, what that means is our models will no longer be biased up or down. As long as we have an accurate forecast of behind-the-meter solar generation, our load forecast should be accurate. So that was the goal. Now, modeling challenges, not certainly the easiest thing in the world to do, but you can do it. Number one thing is you need an historical time series on behind-the-meter solar generation. And in our case, since we're doing modeling for the system operators at the 15 and potentially in the long run we're going to do it at the 5-minute level, we need 5-minute level time series of historical behind-the-meter solar generation. We will also need 5-minute level behind-the-meter solar generation forecast to help drive our load forecast. So what we did with the initial one is we had good estimates of the aggregate installations. We knew roughly where they were in terms of geographic footprint. We could use either our cloud cover with some solar insolation data that we could get from NOAA, or if the weather service provider gave us solar irradiance directly, we could use those numbers directly. So, or as the CalISO has done recently, they have contracted out with an external provider to give them that time series. So once you have that, you can then, it becomes just like any other explanatory variable. You put it in your model, and what you're hoping for, and in principle, the coefficient on that variable should be -1. In other words, for every megawatt of behind-the-meter generation that we produce, that should be 1 megawatt less of load. So we're hoping to get a -1. It turns out in practice, for the sort of prime sunshine hours from 9 to 3 p.m., that's exactly what we get. Not exactly 1, but pretty dang close. We're usually in the 0.92 to the 1.1 range. So it works very, very well. This whole approach has proven itself not only here in California. Recently I just spoke with someone at the New York ISO. They've tried it, and it seems to be working well, and has worked well in Australia. So the approach can work. The challenge that we're seeing with the direct modeling approach is for the non-sort of prime time hours, so from, say, 5 o'clock in the morning to 9, and then from 3 o'clock in the afternoon to, say, 7 or 8 o'clock at night, it's really hard to hang a -1 coefficient on that variable. And the conjecture at this point is what's happening is the amount of solar generation volatility that occurs in these sort of off-prime hours gets swamped by the overall volatility of the loads that you're trying to fit to. So we're going to have to think through this problem and try to come up with a way of getting it to work for all hours of the day, not just for the prime time. But in lieu of that, given that there are some challenges, you can go a different route. And so the different route is to reconstitute the load data. And effectively what we've done is we have the same problem. We still have to construct a historical time series of behind-the-meter solar generation. But once we've constructed it, we can effectively impose a coefficient of -1 by simply adding back that estimate of behind-the-meter solar generation. We just add that back to our net loads. Again, we can then model the total, so that should be gross loads at that point. We model it using the same load forecasting models we've used for years. And then once we get a forecast, we would subtract off the behind-the-meter generation forecast. So this solves the problem of trying to get a good coefficient, a coefficient of -1 or close to -1. It solves that problem for us because we're effectively imposing it. What I don't like about this approach is we're not allowing the data to speak. We are telling the data this is what's going to happen. And so there's pros and cons. Certainly the easier approach is to reconstitute the load data. The more elegant approach is to model it directly. Okay, so where are we going with all this? First off, the number one thing we're working on is we're trying to figure out how to handle those sort of swing hours. How do we handle the time periods when the sort of volatility of the solar generation starts getting swamped by the overall load volatility? So that's the first thing we're working on. The next thing we're going to have to do is currently we do all of this modeling at the 15-minute or 30-minute level. Well, to make this useful for the control room, we need to press this down to where we're doing the 5-minute level forecast for them. So currently our load forecasting system that produces 5-minute level load forecast from 5 minutes ahead out 10 days, what we're going to do is enhance those models, those 5-minute models, to have the same sort of variable for behind-the-meter solar generation allowability at the 5-minute level. If we can do that, and we can do that accurately, then we can give the control room within our forecast that are going to reflect within our movement to cloud cover. And that, at the end of the day, is the thing that's going to help them reduce the amount of essentially backup generation, fossil fuel generation they're going to need to match this sort of volatility and loads that are coming from the behind-the-meter generation. The other thing, everything we've done at this point has been a very high level in terms of big geographic footprints. The next question is, can we push this framework down to sort of substation or transformer level, where then instead of being a sort of a transmission system operator, we want to be able to provide accurate load forecast to distribution system operators where they are working at a much lower level, substation transformer level. So that's another area of research we need to play out, see how it works there. The other thing we're looking at, in fact, we'll be doing that over the next year with the California ISO, is what are the load forecast accuracy gains by using an externally sourced forecast of embedded or behind-the-meter solar generation versus just simply relying on the cloud cover forecast that they currently get. So we're going to be looking at that next year. Once we have the results there, we'll certainly be willing to share those with everyone. And then finally, the other thing that all of this is bringing to the table, and all of this meaning wind and solar generation, grid connected, behind-the-meter, what that effectively is doing to the control room is they need a more or a better forecast of what the load uncertainty is. So there's, in the past we worried about there's traditional load uncertainty because of behavior in human beings and because the weather forecast is wrong and all those things. We could capture that and we could give them sort of an upper and lower bound forecast around our point forecast. Well, now we have to bring in the uncertainty that is attributed to the wind and solar generation forecast. So it extends our idea of how to build sort of confidence intervals around our load forecasts. So those are sort of current as well as future research directions where we're taking this work. Okay, so I'm going to open this up for questions. So if you have a question, feel free to use the Q&A box, and Becca will manage those. Once she has the questions, she'll go ahead and read those over the line, and then I'll go ahead and respond. Now, while Becca's putting that together, this was just the first of 5 talks we're doing on these analytic webcasts. Here's the next series, the next set, and the dates and when they're going to be done. If you're at all interested in analytics from the power or gas side of things, I recommend sitting in on these. There's some very good information, and almost all of these are very leading edge sort of topics. So questions?
Yeah, one more thing I'd like to add to that too, Frank, is the URL to register for this webcast. We created a site on our website. It's itron.com/analytics webcast series. Analytics is plural. So www.itron.com/analytics webcast series. And I don't have any questions on the Q&A tool right now, but I do believe everyone was kind enough to mute their lines. So if anyone would like to unmute their lines and ask questions aloud, we can field them that way as well today. Frank, you must have done such a great job of explaining it.
Maybe we should unmute the lines and see if we can see if anyone's snoring, because that probably put them all to sleep.
I doubt that. I think everyone has muted themselves for this one. We're having some audio issues at the beginning. So please unmute yourself and ask aloud if you'd like.
All right, well, if we don't have any questions now, that's fine. If you do think of something and you'd like to, feel free to reach out to me. I'd be happy to answer.
I have a question. I'm sorry. This is Dominion Virginia Power. Thank you for this presentation. It was very useful. But remains the question how normally we can measure or have like accurate measure for the behind-the-meter generation to start with. Like for us, for example, go ahead. Sorry.
Go ahead.
Like for us, we were trying to do something similar to what you were saying, given what you presented was far ahead of what we were thinking about. The first challenge we have faced is getting those like behind-the-meter generation load numbers, which was very difficult due to the lack of measurement. Unless you know exactly all the solar units in your territory and their nameplate and also the hourly scalers to have kind of an idea how much behind the meter is out there, it's kind of difficult to kind of put that into a modeling framework if we don't have like some data we can trust. So just I'm asking the question how you advise to do that.
Well, it turns out you don't have to be perfect. I guess that's the answer. And that's the nice thing about the direct modeling approach, because what we're dropping in is our best estimate. And then the statistics, the coefficient that gets hanged on that variable, is going to make up for anything that you don't know. Now, I understand that that is by far and away a difficult problem. It's not easy by any means. But you can go, it's surprising, and actually I'll say this, we've tried the same approach in Australia, in Belgium, California obviously, and just recently in New York. And in all cases, except for California, almost everyone else had very little information about what the install base was and where it was. But in all cases, given the best estimate you could, and given cloud cover as the best, measure for things moving in and out, it was surprising to find how many times the estimated coefficient comes pretty close to -1. So even though you have an estimate and it's not perfect and it's not based on measurement, the statistics themselves will recognize that there's something there, and it will hang a coefficient on it. Now, if the coefficient isn't close to 1, maybe it's 10 or maybe it's 4,000, then that would suggest you need to go back and refine your estimate. I think here's the issue. You can't ignore the problem. And granted, we don't have direct measurement, so that would be ideal if we had direct measurement. But the answer is, since we don't have direct measurement, can we do something better, or at least second best solution? And for the most part, you can. And what we have seen to date, at least in those examples I described, it works very well.
Thank you very much.
Not perfect, but it works.
I hear you.
Hello. I have 2 questions.
Mm-hmm.
Yeah, I'm in from Fortis BC. So the first question is your forecasting accuracy directly dependent on the accuracy of the cloud forecasting?
Are you asking me, does cloud forecast impact our load forecast directly, or the?
Yeah. And how can we be assured that we have a good cloud forecast?
Okay. So again, we have done nothing but used the cloud cover forecast that comes with, the same package that you get your temperature forecast, humidity forecast. So we're just using the hourly cloud cover forecast that we're getting, that all these system operators were getting anyway because they were using it for doing load forecasting. It turns out on a large geographic footprint, that's probably all you need. Because we're not trying to forecast, again, this is where on a large geographic footprint, we're not trying to forecast every single home. What we're just trying to capture is, on average, over this footprint, what is the amount of solar generation, up or down? And the cloud cover forecast blended over, say, 3 or 4 weather stations does a pretty good job. So I'll give you a little bit more example specific. Let's say we trying to forecast loads in the Los Angeles Basin. Los Angeles Basin is pretty big. It's, call it 100 miles by 100 miles square. What we'll have is currently we have 3 weather stations, one by the coast, one in the middle, and one at the far east side of that. We take the cloud cover forecast from those 3, we kind of weight them together, and we've used that cloud cover forecast, and it appears, at least based on the statistics, it appears that that's sufficient. That's all we need. Now, all the work that you see in terms of solar generation forecasting, that's very powerful stuff. But again, most of that's oriented towards trying to forecast, generation out of a particular plant, which is a single point in a location. I think what happens when we're doing load forecasting, because we're already modeling at a fairly large level, when you have doing it to support load forecasting, having cloud cover that spans over a large region is pretty good. Because if it's relatively cloudy that day, it's going to be relatively cloudy everywhere in the basin. If it's relatively sunny, it's going to be relatively sunny over the basin. Now, is it perfect on days when it's partially cloudy and you got little puffy clouds rolling through the service territory? No, not at all. But yet at the same time, I don't know if anyone any commercial vendor or anyone has been able to nail the puffy cloud problem. So if you're worrying about puffy clouds over a 100-mile square, that you could worry about that problem, but I don't know if there's any tractable solution at this point. What you can do is handle the cases where it's either all really cloudy or really sunny, and we'll worry about the puffy clouds as we'll just hope the model can handle it.
Yeah, thanks. And the second question is that does Itron have any projection of the behind the meter generation level, let's say in the next 5, 10, or 20 years?
Oh, in terms of
something like this, on your website.
Projections in terms of what the penetration is going to be, the saturation of it. We certainly can do that, and there are groups at Itron. The consulting and analysis group does that kind of work. In fact, George Simons, who's probably who's giving the next presentation, would be a good person to contact on that. So yeah, that would be where we're doing long-term projections of what the penetration would be. Certainly, he can help you with that.
Yeah, because in our British Columbia, or Canadian or British Columbia context, it seems that people try now to take distributed generation serious, something like serious. So, it's interesting.
It's at least for our clients who do system operations, it is serious. They're seeing it. It's impacting their ability to keep the system within tolerance on frequency. And so we have to, because we provide them load forecasts, we need to take care of it. We have to handle this problem. But yes, I think it's not everywhere, right? I mean, are we going to see deep penetration of solar panels in the tips of the world? Probably not. But there are certainly areas where there has been both government financed or at least government supported penetrations that are pretty significant.
And typically, utilities would have some reserve for integrating wind. So how can they use this to cope up with inaccuracy in the distributed generation? Can they cover this reserve?
So in the case, I'll give you an idea. So at the California ISO, our system produces forecasts not only for loads, and it's not only loads adjusted for the behind-the-meter solar generation, but it also provides forecasts, and this all goes to the system operators. It provides forecasts for each wind farm and each solar plant, so throughout the state of California, and that runs, every 5 minutes those forecasts get updated. So that is a place where in the control room, having real-time forecasts of all the renewables, both the behind-the-meter as well as the grid-connected, is being used to control the systems. And so there's a lot of pressure to try to get all those forecasts as accurate as possible, because the more accurate you can be, the less backup generation you need. And so that's really sort of the role, or the role of forecasting at this point, is trying to come up with as accurate forecasts of these renewables as we can.
Okay. Yeah, I agree. Okay, thanks a lot. Yeah.
We have a couple questions that just came in through the Q&A tool. You might have already touched on this a little bit, Frank, but how is cloud cover determined numerically? Okay, so cloud cover, it depends on where you are in the world. It's either going to come in on a 0 to 100 scale, or it comes in on a 0 to 10 scale. It effectively means the same thing. 0 means it's totally sunny, and 10 means it's totally cloudy. Now, can you get refined on that? You can. And what some of our operator clients, or our TSO clients, are doing is they've asked the weather service provider to give them a solar irradiance forecast rather than a cloud cover forecast. The idea is with solar irradiance, they are taking into account not only whether it's cloudy or not, but the density of the clouds. So solar irradiance is a measure of how much solar energy is striking the Earth's surface, and that's becoming a more useful measure for them. Just a remind everyone to please mute their line.
Yeah, I have one question, if you may, but there is some using going on. Correct me if I'm wrong, if I understood very well, one of the underlying assumption or the implied assumption in the example you showed us is that the true demand is observed only when it is overcast, like this 1,000 megawatts, for example.
Mm-hmm.
And what if, like, when it is sunny, instead of 1,000 megawatts, it's 1,100 megawatts?
Sure.
So how do we square that with behind-the-meter generation if we believe that under sunny conditions, behind-the-meter generation will kick off?
So here's the thing. Remember, we're dropping that estimate of behind-the-meter generation into a full-blown load forecasting model. So that full-blown load forecasting model is taking into account day of the week and seasons and weather and all that. So our actual forecast, the exercise is really just a simplified exercise. But the reality is our load forecast model is taking into account what's going on with demand for power.
Okay, thank you.
Mm-hmm.
Okay, we've got a couple more questions staying on the cloud theme. You're recommending the use of cloud cover forecasts. So how many load forecast zones are you using? What areas are you using, and what is the size?
So where this has been used, the size of the zone, the load zone that we're trying to forecast, is pretty much about equivalent to sort of the Los Angeles basin. So about 100-mile by 100-mile square kind of thing. And they vary. Some are smaller, some are larger, but just think of that as sort of a good rough idea. So that right there you already have, because that's a very large span, you already have a lot of averaging. Like there will be people on the coast where it's cloudy and they're not generating anything, where people inland are generating. But on average, and that's what we're going to capture, on average we're pretty close. Now, I'm advocating cloud cover only to the extent that you have nothing else to use. And that's where we were. We started with all we had available to us was cloud cover. So we said, okay, let's try something. Let's try to construct a time series using cloud cover and see how close we can get. And it turned out it worked pretty well when you were doing a large geographic footprint. Now, if you came to me and said, I want to forecast the solar generation on this house, cloud cover forecast that you get from your weather service provider is going to be a lousy measure, because they provide cloud cover for a large geographic area, not for a very specific point. And that's where the other techniques, the eye in the sky, or the sort of mesh metering approach, or even the satellite imagery approaches, are going to be more accurate in terms of forecasting cloud cover over a very specific point. But when we do load forecasting, we're load forecasting of a large geographic footprint, and so the cloud cover appears to work very well.
Great, thanks, Frank. Okay, one more we have on the Q&A tool. Will you be looking at behind-the-meter storage in the future as well?
That would, the approach effectively would apply to anything behind the meter, and that includes if we start having electric vehicles. We're going to have something there. But yeah, so storage would be a thing. Now, that would make a lot of sense if we were down to the transformer or substation level forecasting. We definitely want to take into account storage, because that will have a very immediate impact on the loads, or what are the measured loads at that level. Now, will storage at this point, storage is not significantly present, but eventually it probably will be for again, 100-mile by 100-mile square territory. The amount of storage that's in the LA basin is probably a blip on the radar map at this point. If that grows significantly, like the behind-the-meter generation has, then yes, at some point we're going to have to take that into account.
Okay, and here's another one. Do you consider the sun's angle in your models?
It turns out that we do, and it's not only the sun angle in the course of the day, but it's also the sun angle throughout the course of the year. The good news is, all those formulas, if you are available, right? Newton figured out most of this stuff. It turns out that NOAA on their website, they have a spreadsheet where you type in latitude, longitude, and it'll do all the calcs for you. So what we typically do is we'll use NOAA because they do a very detailed calculation. We then take their numbers, which are sort of solar insolation at solar noon, and then we'll spread that across the 5-minute intervals in order to support 5-minute, 15-minute hourly modeling. But all that stuff is very tractable. You can get your hands on all of that.
Great, thank you. Any other questions?
Okay. Well, like I said, if you have follow-up questions, feel free to, you can email me. I'll be happy to address them. I appreciate your time, and I highly recommend sitting in on some of these other presentations that are coming. Have a good day.
Thank you.
Thank you.